Hey there guys, I'm going to show you guys this method of solving a system of equations using a matrix. We are doing this a little bit out of order. Would normally do, I think this is going to be a lot easier to teach you guys this with a video than to teach you what we're supposed to do on this Friday. We're going to do two videos. The first part will be how to find a determinant and an inverse. So I'll go down through number 3 here on that video, and then on the second video I'll talk about how we're going to use it to actually solve a system of equations. And we are going to just look at this with the smaller two variable system of equations. Finding determinant and inverse of a 3 variable or like a 3 by 3 matrix is quite a bit harder than finding a variable, one for a 2 variable. Or a 2 by 2 matrix. So just FYI. So tomorrow's going to be the 30th. What is an inverse? So you guys know all about inverses already, and this is totally right to ask you guys, what are inverses? And usually you're thinking like opposite or reverse or reflection, like so. These are just things students have told me in the past, or people typically think when they hear about what an inverse is. The way I think about what an inverse is it's something that undoes something else. So one of the ways we use inverses a lot in math is like with inverse operations. When you're solving an equation, it says 3x plus 2 equals 5. Like we use inverse operations to do that. So it says plus 2, so I'm going to subtract 2. And then it says times 3, so I'm going to divide by 3. Those are inverse operations because they undo the operations that are there already. So something that undoes something else. Kind of the way that we're using here. What is an additive inverse? So things like what would you add together to undo things? Like negative 3 would be an additive inverse of positive 3, or 12 and negative 12 would be additive inverses. And when you add additive inverses together, you get the additive identity, which is like why we call it the identity is because it gives the whatever back. So like what do we add to something to get the same answer back? We add 0 to something to get the same answer back. 3 plus negative 3 is 0, and 12 plus negative 12 is 0. So when you add additive inverses together, you get the additive identity. We're mainly going to talk about multiplicative inverses today. That's a fun word to say, multiplicative. So like what are multiplicative inverses? It's like, what's the multiplicative inverse of 3? Well, I multiply 3 by to undo 3. Well, it's just 1/3. 3 times 1/3, right? It undoes it. And multiplicative inverse of negative 12 would be negative 1/12. And we multiply something by its multiplicative inverse, we get the multiplicative identity, which is 1. And it's called the identity because if we multiply something by 1, we get the same thing back. So it keeps its identity. So it turns out that matrices also have inverses and identities. A little bit of notation here. So I know we talked about this yesterday. So that symbol there is just, we would say it's matrix A. So it just stands for some matrix, whatever it is, whatever's inside of there. But it's just matrix A. And then how we write the inverse of matrix A. So there's two ways to do that. So matrix A, but then with the negative 1 exponent here, right? We use that symbol for, again, not to say it raises to negative 1 power, but to stand for the word inverse. So another option would be just a capital A with the -1 exponent on there. So both of those symbols would stand for the inverse of matrix A. You will typically see me use this one. And then an identity for matrix. So we're mainly going to be looking at 2x2 matrices. This is something you guys would actually, you'll see when we do the next lesson, which would normally be the previous lesson, and you would recognize it a little bit more. So a 2x2 matrix, it's going to have 4 elements in it. So the identity for that is going to have a diagonal of 1s, and the other 2 elements are 0. So it would always be the start at the top left, go to the bottom right with the 1s. If we were having to look at a 3x3 matrix, like what its identity is, very similar. It's going to have 9 elements in it. So we have a diagonal of 1, so the center is 3 rows, and then everything else is 0. We aren't going to really look at this one, but this is something you'll see in the next lesson when we're doing the reduced row echelon form. So this is what the identity matrix looks like. So basically, if we were to multiply this matrix to some other matrix that it's multipliable to, like we talked about, it would spit the same matrix back. So we can mess around with that later if you want, but it's just our goal is going to be to end up with something like this and look for that identity. So in order to find the inverse of matrix A, or same thing, just different notation again, I'll usually this one. If it exists, so not all matrices have inverses, we need to know something about that matrix. So every square matrix, so these are square matrices, right, as opposed to like a 1x3 matrix, which is not a square, it's a rectangle. So 2x2, a 3x3, a 4x4, a 1x1, 5x5. We're going to be focusing on the 2x2s. So every square matrix has a number or value associated with it. And it's called the determinant. Some of you guys might know about the determinant in regards to the quadratic formula. It's also called determinant, but it's a different thing. And the way we write the determinant is that you can either do capital A, and then you would do essentially what looks like absolute value lines. So I'm just going to kind of accentuate them so they don't look like, I don't want them to look like L's or 1s or something like that. So I'm just making them a little bit longer than, so kind of like that. Or you can use lowercase Greek delta, which is like this squiggly D thing. I'll try it again. So it kind of looks like that. So delta A, like that would some determinant of A. Or you just say det A. So this is the way you'll see me do it, just because that's the most clear to me. Again, when I write inverse, I'll write it this way. So all those stand for determinant. That's the one I'm going to use. So all those are different ways of representing the determinant. Of matrix A, right? And so we could do determinant matrix B, or determinant matrix T. Like it all doesn't matter, but I'm just using A here. So if matrix A looks like this, so again we're looking at 2x2. I'm going to use letters here instead of numbers or anything else. It's a little easier to see how things move around. So it's 4 elements in it. I'm going to say A, B, C, D. Okay, so if the matrix was arranged like that, then the determinant of A is a very simple formula. And it's something you guys will need to know. It's very simple. Like I said, is A times D. So A times D, and minus, always minus, B times C. So I can very simple formula. If I want to figure out what the determinant of this matrix is, we take A times D, then minus B times C. And of course, with subtraction, the order you do that in does matter, so just be aware of that. Okay. So practice that a couple times here. So just I want to look at the top left to the bottom right. So here's my, and I'm going to write this out a little bit more than normally I would, but so negative 1 times 9 minus, and then B times C, which is 3 times negative 2. Of course, negative 1 times 9 is negative 9 minus, and 3 times negative 2 is negative 6. And of course, minus and negative, same thing as addition. So the determinant, since this matrix doesn't have a name, I'm not going to put like determinant of A, that's just the determinant of this matrix. So let's say determinant equals negative 9 plus 6, which is negative 3. Yep, there's its determinant. So what I would normally expect to see from you guys as far as like work level, just kind of show me, of course you wouldn't be highlighting things, but you can do the multiplication in your head. So 4 times negative 1, so negative 4, then minus, and 6 times negative 2, so negative 12. And so then our determinant would be 8. I would just prefer that you guys show your work so I know like you got 10 or something like that, and all of a sudden like I know where that's coming from and I'm able to help you rather than just having your answer there. Here would be a good idea for you guys to stop and try doing C and D on your own. I did change the element here on D to 6, and then check your answers against mine here in a second. So time to do that. So part C here, the determinant is negative 2, and part D here, the determinant is 0, as long as you change that to a 6. So hopefully those worked out for you. If not, check with somebody, see what's going on. So what do we do with determinants? So as long as the determinant of A, or whatever matrix you're looking at, is not 0, then the inverse of A exists. So we use the determinant to, 1, know if there is an inverse, and 2, it's going to be part of how we find the inverse too. So, okay. So again, so you need to know is how to calculate an inverse, and that's a formula you'll need to know. And then this next little process here, it's not a formula per se, it's more about like moving numbers around. This can be a little tricky. It's not hard, it's just tricky. Again, this is something you guys will need to know, like how to calculate an inverse. So starting off with matrix A, again, the same arrangement as before. So if this is matrix A, then the inverse of matrix A is equal to, I guess it's kind of like a formula, but so 1 over the determinant. So you've already found the determinant to see if there's, to see if you're even going to do the problem, right? So you've already done that work, right? So you also need it as part of your calculation. So 1 over the determinant times, so it's just going to be scalar multiplication. So this is kind of the tricky part. So we have it's going to be times D and A are going to switch spots, and then B and C are just going to change their signs. So when I write negative B like that, I don't mean negative B, I mean the opposite of B. And C is also going to be the opposite. So again, they're not swapping signs, like they switch signs with each other. They are changing their own sign. So if B was already 6, then this number now would be negative 6. Or if C here is negative 2, now that would be positive 2. So like whatever the sign is. These are both positive, so they're both become negative. They swap their own sign. They become the opposite of what they were. So that's the part that's kind of tricky, right? Is remembering like kind of the motion, like these two switch places. So I'm just kind of writing that out, like A and D swap places. And B changes its sign. And then C also changes its sign. So getting that motion down, like which things change, how they change, is the kind of tricky part. As long as you're careful that it's not difficult to do. Right. So we're gonna try to find the inverse of matrix A here, if it exists. Right. So that's always an option. The problem isn't doable. So the first thing I want to do is calculate the determinant. And you kind of want your spacing here. I'm going to calculate the determinant down here. So the formula is A times D. Which is, right color here. A times D, so that's -2, and always minus. And then C times B, so which is 4. So I get -6. So since that's not 0, right, that means the inverse exists. So let's kind of make a little note there. So we're going to keep going. Okay. So I'm going to take the determinant, right? I'm going to put 1 over the determinant, so 1 over -6, so that number went there, times, so remember, A and D are going to swap places, so I've got -1 here now, I've got 2 here now, and then 4 is going to change its sign, so I've got -4, and 1 is also going to change its sign, so I've got -1, and we'll just distribute that 1/6 through there. I really suggest like not using decimals or anything like that. It's going to make things messy. Just do the fractions. It's nothing crazy. -1 times -1/6. So I just want your sign here. Right? It's just 1/6. Same thing here. -1 times -1/6 is 1/6. -4 times -1/6 is -4/6. Or sorry, +4/6. Then 2 times -1/6 is -2/6. And then you would reduce anything that's reducible. So 1/6 and 1/6 are not reducible, so let's leave those alone. 4/6 is equal to 2/3, and -2/6 is equal to -1/3. So there is the inverse of this matrix. And so the idea is if we took those matrices and we multiplied them, so if I you guys don't need to do this, but this is just the idea. I multiplied that matrix by this matrix. 2/3, we go through the whole rigmarole of multiplying like we learned yesterday. If we go and do that, we would end up with the identity, right? The inverse is going to undo that, so we would end up here. Oops. Remember, matrix multiplication, the order doesn't matter, so when you do that, you would need to take this first times this second, and then 0. Okay. But you would end up with the identity. That's the idea. Something that's going to pop up later is that this right here actually might be an easier form of the inverse to use. So I just call that kind of my pro tip here. So you might find it easier. To use when the denominators are all the same. So if you're just calculating the inverse, you don't need to worry about this. It's when you go to use the inverse, actually solve the system. It might actually be easier to use it when the denominators are the same, just because of some fraction, addition, stuff you're going to have to do. So it's easier to add fractions when the denominators are the same versus when they're different. So just something I would recommend, and I'll show you that when it comes time. Practice doing that again. So I want to, first step, I want to find the determinant of some matrix B here. So find the determinant of B. Take A times D, so -2, always a minus, and then 3 times 1, so 3. So determinant B, so -2 minus 3 is -5. So that means there is an inverse. So the inverse of B will be equal to 1 over the determinant, so 1 over -5, yeah, that helps, times, so again, A and D swap places, so we got -1 and 2, and then the 3 is going to change signs, and the 1 is going to change signs, so I got -3 now, and then -1 now. And I'll distribute the -1/5. So -1/5 times -1 is +1/5. Same here, just coincidence that it happened both times. For those, that first column was the same. And I got +3/5, and then -2/5. And none of those are reducible, so there's my inverse. And this last one, we're going to do that, so find the determinant of C. So again, taking 2 times 8, which is 16, minus 4 times 4, which is also 16, so that equals 0. So if the determinant is 0, then there is no matrix, no inverse. So, because if it was 0, that means we're putting 0 down here, and we can't divide by 0. So, you just say that inverse of C does not exist. So that was easy. Alright, so that's how you find an inverse, how you find the determinant, and then on the next video, just so it's easier to upload, I'll show you how to solve the system of equations using this method with this tool. So.